Welcome to example 4. We have a certain cathode metal used in a photoelectric experiment, and we're given various points in here. 3 volts for a 300 nanometers, so that's the stopping potential. So let's actually just make a table here first. So over here I'll put the stopping potential V sub S in volts, and we have 3 volts here. And then for that particular wavelength, this is the wavelength lambda in meters. And this is 300 nanometers, and we have 2.0 volts, and we have 400 nanometers, and then we have 1.0 volts, and that will give you 600 nanometers. And we're asked to plot a graph, which is actually shown already here, and determine a number of things. We have frequency measured in hertz. So to determine the frequency here, which is actually already plotted for you, we would use the speed of light divided by the wavelength. So for example, if I wanted to find the first one here, I would use the first wavelength. Speed of light is 3 times 10 to the power of 8 meters per second divided by the wavelength, which is 300 times 10 to the power negative 9 meters. If you work that out, you'll get a frequency of 1.0 times 10 to the power of 15 hertz. So over here we have 1.0 to the power of 15 hertz. Then we have the next one is going to work out to 0.75 times 10 to the power of 15. And the next one over here is 0.5 times 10 to the power of 15. Okay, you're asked to find out what the work function is, as well as finding the experimental value for Planck's constant, h, and then the cutoff wavelength, that maximum wavelength which electrons are being emitted. Now, hopefully you recall the photoelectric effect equation, which states that the maximum kinetic energy is equal to the difference between the incoming photon energy, h times f, minus the amount of energy to knock out those electrons, which is called the work function. Once again, this is the photon energy, and over here this is what is called the work function, and this is our maximum kinetic energy of the electrons. Now, you learned earlier, hopefully, that the maximum kinetic energy can be determined by knowing the stopping potential. It's equal to Q times V. Think of this kinetic energy as equal to the electric potential energy. So the Q in this case is actually E, because it's an electron that's being stopped, and then the V is the stopping potential. You can use a V sub 0 or a V sub S for stopping potential. So we're going to replace that into this equation. We'll have E V sub S equals HF minus the work function. Now you might be seeing where I'm going with this. I'm trying to relate this equation. You see, this is a line, a linear fit, and equational line is of the format of y equals mx plus b. And on the y-axis we have the stopping potential, V sub s, and the x-axis we have the frequency. So hopefully you can start to see how this relationship is showing up here. I'm trying to fit the theoretical equation to the experimental curve that's plotted here. We've got frequency, which is right here on the x-axis, and then on the y-axis we have the stopping potential, which is right over here. We want to get it as written as y equals mx plus b. So let's get this all by itself. So we're going to divide everything by E here. And so you'll get now the stopping potential is equal to h over E times F minus the work function over E. And so you now hopefully can see this in the right format. There's your y, and there's your x, and this is our y-intercept, which is down here. This is nicely written in our y equals mx plus b format. So therefore, if we want to find out what the work function is, which is this is the work function here, we need to find out what the y-intercept is. And you can see that right on the graph. So the y-intercept in this above graph is equal to -1 volts. And we know that y-intercept is equal to the work function divided by E. So that's equal to -1 volts. All right, we have a negative sign here and a negative sign there, so really we're just going to have just a positive in the end. Now, solving for the work function will end up, when we cross multiply here, we're going to get negative, or we're just going to get, actually no negative. Let me just erase that. You're going to get 1 electron volt is your work function. You could also write this in terms of joules. 1 electron volt, if we were to convert this to joules, we would multiply by 1.6 times 10 to the power negative 19 joules for every electron volt. So this work function is equal to 1.6 times 10 to the power negative 19 joules. So there's our first answer here. Okay, now let's move on to finding Max Planck's constant. How are we going to determine that? So you look at your equation once again, and you're trying to find Planck's constant, which is h. And you can see h is this right here, which is the slope. So we have to realize that the slope of your graph is theoretically equivalent to Planck's constant divided by e. So you'll need to do over here and find out the slope of your graph, roughly speaking here. So the slope is the rise over the run. The rise would be 3 volts, I guess. We'll pick it from right at this point down here. And then the run will be 0.75 times 10 to the power of 15. So over here we could write that. If you do this on your calculator, 3 divided by 0.75 times 10 to the power of 15, or you can probably do it in your head, it's 4 times 10 to the power of negative 15. And this is measured in a volt over a hertz. And remember, a hertz, 1 hertz, is a cycle per second. So a hertz is just really 1 over seconds. And so when you bring that up to the top, you'll get seconds here, is equal to h over e. So rearranging for Planck's constant h, we would have to take 4 times 10 to the power negative 15 volt seconds, which is the slope, and then multiply by the charge of an electron e, which is 1.6 times 10 to the power negative 19 joules. I always like to double check that my units are making sense here. So I'm going to change these volts because I know a volt is equivalent to a joule per coulomb. And so we get joule per coulomb here. And I just realized I made a little mistake. Obviously the charge of an electron is not measured in joules, it's measured in coulombs. So let's put a C over here now, and let's see our cancellation. The coulombs here are canceled out with these coulombs, and you're going to get an answer in joule seconds, which is the units of H. So H will be equal to 4 times 10 to the power negative 15 times 1.6 to the power negative 19. And this gives you a value of 6.4 times 10 to the power of negative 34 joule seconds. Now, you could also, by the way, if you'd like to put it in the other notation, you could have just left this e in there, and you could have had 4 times 10 to the power of negative 15 in electron volts times seconds. That's another version of the same constant. All right, there's Planck's constant now. Okay, we have one more piece. We have to find the threshold frequency. Actually, more importantly, we're looking for the cutoff wavelength. So what is that minimum wave or the maximum wavelength you have to have so that you will get photoelectrons being emitted? All right, so we're going to find this particular x-intercept. The x-intercept in our graph represents the threshold frequency, which I'm going to call f sub 0. So you can see over here on the graph, it is 0.25 times 10 to the power of 15 hertz is our threshold frequency. Now, we could find our cutoff wavelength, all right, lambda c for cutoff, and remember that v equals f lambda. So it would be equal to the speed, which is the speed of light, divided by the frequency. So that's 3 times 10 to the power of 8 meters per second divided by this x-intercept frequency here of 0.25 times 10 to the power of 15 in hertz, which is 1 over seconds. I get an answer of a cutoff wavelength of 1.2 times 10 to the power of negative 6 meters. Or if you want to put this into nanometers, you can multiply by 1 times 10 to the power of 9 nanometers in 1 meter. And this will be a cutoff wavelength of 1200 nanometers. Okay, and that's it for this example.